Okay. So let's do the existence part. Okay, so existence of primary decompositions. All right, so so the theorem is if A is Noetherian, A is Noetherian, and I is an ideal in A, then I admits a primary decomposition. Okay, and the trick here is we're going to use something. We're going to do something a little bit different. So let me just do a definition here. Okay, so I'm actually not going to do a primary decomposition. I'm going to do it into what we're going to call irreducible ideals. So let me give you a definition. And irreducible ideals will be primary. An ideal I is irreducible if and only if I is equal to I1 intersect I2, with these two other things are ideals, then I is equal to I1 or I is equal to I2. Okay, so this is what an irreducible ideal is. Okay, so let's prove a lemma now, or theorem. Okay, the lemma is that if A is Noetherian, and I, let's say in Q, in I, or Q in A is irreducible, then Q is primary. Okay. So let me just give you a warning here that the converse of this statement does not hold. Okay, so let me give you an example. So the converse does not hold. You could have a primary ideal, so that the intersection, you can have the intersection of two primary ideals. Intersection of two primary ideals can give a non-trivial primary ideal. Okay. Okay. So I had an example, but where did my example go? Well, anyway, well, let's just do the proof. Okay. Okay, so let's do the proof of the theorem. Okay, so suppose that so we're going to use the Noetherianity assumption that Q is irreducible. Okay, so we will show that the only zero divisors, excuse me, so the only zero divisors of A mod Q are nilpotents. Okay? Okay, so here's what we'll do. We'll suppose that xy is equal to so xy are in A mod Q, both non-zero, and that xy is equal to 0. Okay, so in the quotient, right? So we will show that x to the n is equal to 0 for some n sufficiently large. Okay, so we're going to show that. So I'm supposing that we have zero divisors, and now we're going to show that the zero divisors are nilpotent. Okay, so we're going to use Noetherianity. Okay, so we consider, since we're going to be doing Noetherianity, you expect there to be a chain of ideals, and so here's the chain. So we consider the chain of ideals, where we take the annihilator of x. This is going to be contained in the annihilator of x squared. And this is going to be contained in blah, 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 blah. And this is going to be contained in the annihilator of xn. Okay, and then at some n, it's going to kick in so that these things are the same. Right? This is going to be the same thing as, annihilator of xn plus 2. Okay, and so at this stage, this is where the Noetherianity kicks in.
We proved those were ideals a while back, huh?
Yeah. It's not hard to show that they're ideals. Yeah, to show that they're ideals, if something kills it, right, then a multiple of it is going to kill it. And then if two things kill it, right, then if you add them together, they're both going to kill it as well.
Yeah, right. Okay.
Yeah. So yeah, that's all there is to it. So this kicks in. So you're going to have, and so we're going to suppose that these are all not equal, right? And then at some stage they're going to just start to be equal. Okay. So we claim that x to the n intersect y is equal to 0. Right? So by irreducibility, this implies, so I'm copying my note here. This implies x to the n is equal to 0, or y is equal to 0, which implies that x to the n is equal to 0. Okay, because we suppose that y was not equal to 0, right? Since y was not equal to 0. Okay, so by the way,
where was irreducibility?
How do we? Yeah. So this is irreducible. So let me just say that. So I guess did we show that this zero ideal should be irreducible? Okay, so I claim that this is irreducible by. So do we have like a little lemma that said that quotients? So the zero ideal. So I guess we're implicitly using here that the zero ideal of a quotient is irreducible. So like, okay.
And then I just want to check that irreducible, like you're irreducible if and only if your primary decomposition only has one prime. Is that right?
Yeah.
Or
So
area?
no. You're irreducible. You're irreducible. We're using this definition of irreducible here.
I'm sorry. Okay,
yeah. I think you might have used the word irreducible component in a previous class interchangeably. But this for today, this is what I mean by irreducible.
Okay, cool.
Okay. So this is what I want to say by irreducible today. Just it's a purely ideal theoretic concept. Okay. I think I talked about irreducible components of schemes, but this is about ideals.
I don't know if it's too much of a sidetrack, but if they're when is it that the intersection equals the product?
Like
it's a I1 times I2.
Like rarely in PIDs, for example. So when is the intersection equal to a product?
Okay, there's a containment one way though, always.
Yeah, there's a containment one way. I think if you have IJ is I intersect J, if I don't remember. Yeah, yeah, there's an easy containment. The easy containment is this way. Right? And then the equality appears in, say, the hypotheses of the Chinese remainder theorem. So I think if you have like I plus J is equal to R, it's true.
Oh, right, where they're relatively prime. Yeah, okay, that's right.
Yeah, I think that we have this. Like 90% sure that's true. But yeah, I would check that. But this appears in the hypotheses of the Chinese remainder theorem. You always have this, but you should never think that multiplying prime ideals is the intersection. That's one of the things I want you to take away from this, is that like, that's a no-no, right? Because when you multiply prime, even when you multiply two prime ideals, you can pick up a primary component. And there's an exercise in the homework about this, right? That you can pick up some embedded components from doing that sort of thing.
Got it.
Yeah. Okay. Okay. So this part here, we're gonna need this kind of like a little exercise, I guess. That I forgot to mention here is that if Q is irreducible, maybe I'll put this on the homework. Is irreducible, then maybe I need an if and only if. Q is irreducible if and only if 0 in A mod Q is irreducible. Okay, so I'm pretty sure this is correct. But let me check with me after class, and then I'll say whether or not this is correct. I need to check it. But let me put 90% sure that this is true. Because the proof is we need to use this. Okay? Then if not, I'll add a correction. Okay, so we're using that here. We're doing an A mod Q. Okay, so we're using that this is irreducible. So this is the 0 ideal. If this is the 0 ideal, then we have the intersection of two things by irreducibility. We're going to have this thing is the 0 ideal, or this thing is the 0 ideal, because that's the definition of what it means to be irreducible. In the first case, or in this case, the second case, we suppose that y was not equal to 0, right? That was way up here. Okay, so I guess we should suppose here. Where do we have non-zero? Right? So I suppose that y was not 0. Okay, so we're going to have that. And then, yeah, so that tells us that x to the n is equal to 0. Okay, and that's what we wanted, right? We wanted x to the n to be nilpotent. Okay? Okay. So now there's some more we have to do. Okay, and I need to look at what happened here. So let's just write it out. Okay, so what I'm going to do is I'm going to do, so we already have that x is nilpotent. So I don't know. Oh, okay. So one thing that we have is so we're supposing this claim here. Okay, and we need to justify this now. If we can show this claim, then we're done. Right? That's what we've done. Okay, it remains to show that this is true, right? So we need to prove this claim. So the proof of the claim. Okay, and so to prove the claim, we need to take an element that's in both, right? And we need to show that it's 0. So we're going to suppose that A is an element of x to the n intersect y here, and we will show that it's 0. So we will show that A is equal to 0. Okay, does that make sense? All right. All right. So if A is in Y, which is true, right? Then AX is equal to 0. Okay, this is because we had that XY was equal to 0. Okay, so if A was in x to the n, right, then what do we have? So we have that A looks like, sorry, it keeps going like that. A is equal to x to the n b, which implies that, b x to the n plus 1 is equal to 0, which implies that b is in the annihilator of x to the n plus 1, which is in the annihilator of x to the n, which is equal to the annihilator of x to the n, right? Which implies that A is equal to 0. Okay, because of this equality before. Okay, so so we have this. Okay, so this implies that. So this shows that A is equal to 0. So here, I guess we're using that AX is equal to 0, right? At this stage here. So this input here, this thing here where AX is equal to 0, this is AX. Okay. And so, all right. And so this proves that that x to the n intersect y is equal to 0. Okay. And now we proved our claim, and from our claim it follows that x is nilpotent. All right. So we proved that that Q was primary if it was irreducible, and it depends on the fact that you can check that something is irreducible by checking that the 0 ideal and the corresponding quotient is irreducible. All right, any questions on that? Oh, actually, I did write up the exercise here. Okay, so this is 100% true. Okay, so you guys should check. It's actually not bad. It's just like inverse image, blah, 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 blah. Here, I'll flash it. There. Okay, so now we need to prove uniqueness. Okay. All right. All right, let's do the theorem now. So proof of, okay, so proof of existence of primary decompositions. Okay, and so again, we're using that the ring is Noetherian. Okay, so we need to show, so we will show that every ideal in a Noetherian ring is a finite intersection of irreducible ideals. All right, and so this, I guess it doesn't show the minimality part of this, but I claim that you can get the minimality part just by modifying this. All right, so we're just going to show that again, every ideal is a finite intersection of irreducible ideals. Okay, so what we're going to do is we're going to do the axiom of choice. Okay, so we're going to use the axiom of choice. So S, we're going to take a set, and then we're going to, we're going to do chains, and then we're going to, so let's see, we're going to use Zorn's lemma. Okay, so we're going to look at the set of ideals here in a ring A. So A is going to be a ring. Okay, this is going to be I is not a finite intersection of irreducible ideals. Okay, so this is going to have a maximal element. By Zorn's lemma. Okay, and we'll call this I0. Okay, so this would mean that I0 is equal to I1 intersect I2 with I1 I1 does not contain I, and I2 does not contain I. So I'm reading off my notes here. So let me think about this a little bit. So okay, so what we're going to want to do is we're going to try and find something, an element in here that is, so it's not a finite intersection of irreducible ideals. Okay, so so this is maximal. So we find something smaller in here, right? Then
And wait, what is I?
I is an ideal.
any ideal?
So
I1 does not contain
oh,
I.
0, 0, 0, 0 here. This
okay.
is I0. Yeah, good call. Right. This is I0. So yeah. So what are we doing here? So what we're gonna okay. So if we had this property and I was equal to and we had either one of these containments, then that would show that for every decomposition like this would show that I0 would be irreducible, which would mean it would be its own decomposition. Okay, so this is saying that I is not irreducible. I0 is not. Otherwise, I0 would be an element of would not be an element of S. It'd be its own decomposition. Okay, so now what do we have? So S. Okay, also we can't have S containing I1 otherwise, right? I0 sorry, we can't have S not an element, right? Otherwise, I0 would be able to be written, could be written as a finite intersection of irreducible ideals. Okay, so if you see what I'm saying, so if they're both not contained in S, right? Then what's going to happen, right? Well, that means that I1 and I2 can be written as a primary decomposition, so it can be written as a finite intersection of irreducible ideals. And if they both can be written as a finite intersection of irreducible ideals, then I0 can be written as a finite intersection of primary ideals. Cool? Okay, so if that's the case, so this gives us a contradiction, right? Contradicts the maximality of I0 and S, right? Since we need either I1 and S and I2 and S. Right? So they, yeah, so they both, yeah. So I think I stated that right. So yeah, they one of them needs to not have a primary decomposition for I0 not to have a primary decomposition. All right. And so I think that concludes the proof of this one, modulo the details on this. So, all right, so then check. So I guess we should do this is check Zorn's lemma details here. Okay, and so that is, so you need a bounded chain to have a maximal element outside the, so what do you need for Zorn's lemma? So you said every chain needs to be bounded by an element, right? Not necessarily in the set. Okay, and I don't know that off the top of my head. Okay, so that's all I have for today. I'm getting a phone call. It is probably spam. So if you guys have any questions, I'm going to stick around after class. And thanks for watching.
Thank you.
You're welcome.
Taylor, I just wanted to ask, so you have this I0 by Zorn's lemma.